So for those of you who are just tuning in, this is from the Atcoder Beginner Contest from today. I solved all the problems and I'm going to be going over all the solutions. And by the way, there should be a link to my Discord and my Twitch where I normally do my live streams. I might switch to YouTube or I might keep going back to Twitch. Maybe do some of both. So check those out in the description and feel free to join my Discord to stay up to date on my future streams and future uploads. Okay, great. So let's go over A. So here we have someone playing a game, a classic Atcoder character, and basically we want to see how many more coins they need to get until the next multiple of 100. And if you're already at a multiple of 100, as in this example, you want to go to the next one. So we can actually just look at the implementation for that. Basically A, B, and C for this contest were all fairly straightforward like implementation problems. So you just have to make sure that you don't make any mistakes. So here I read x, I find the remainder when x is divided by 100. So for example, here you have 140, and then that becomes 40. And then I take 100 minus x, which is how much you need to go to the next multiple of 100. So in that case, that would be 60 for this example. And just to check our edge cases, does this work when it's already a multiple of 100? The answer is yes, because this becomes 0, and then this becomes 100. Cool. All right, let's go over B. So for B, it's another, you have to read the problem and carefully implement it situation. So let me just check, is my stream? Okay, cool. So my stream is on Codeforces. Awesome. Okay. So yeah, this is another pretty straightforward like implementation problem. What we want to do is, I'll show the code. We want to check to see if exactly the odd positioned letters are lowercase and exactly the even positioned characters are uppercase. So I just wrote this function here that checks if a character is uppercase, if it's between capital A and capital Z. And then here we check to make sure that like the first letter is not uppercase and the second letter is uppercase, etc. And we make sure that all of those conditions hold. Here we're checking if it's like the first character, if it's this checks if it's an odd position character according to the problem statement, because the problem statement starts with 1. And this checks if it's uppercase. So we check that exactly one of those is true at each point. Every character is either odd positioned or uppercase and not both. Cool. So that's that problem. All right, C. C was kind of an interesting one because it seemed pretty tricky at first, but the constraints are actually quite small. Feel free to chime in the chat if you have any questions, by the way. But for a C, the constraints were pretty small. You only have k equals 10 to the 5th, and n equals 10 to the 9th or less actually means that the number of digits in n is at most 9 or 10. So if we just like do exactly what they say, as here, what we do is we find the digits, we sort them in ascending order, and then we create two numbers, one that's from them sorted in descending order and one that's from them sorted in ascending order, and we subtract them like they said. If we do this every time, this takes like about 10 times k operations. So this is like more than fast enough for this problem. So it's a pretty straightforward implementation problem. Cool. So that's basically it for C. I guess there's a couple things to note here. If you want to convert a number into its digits, you can get the last digit by modding by 10, or whatever your base is, and then divide by 10 to shift all the other digits over repeatedly. This is, I think, the cleanest way to do it. The other way you could do it is by keeping track of different powers of 10. Like and modding and dividing by those, but that's just doing extra work. And then to reconstruct a number from its digits, the nicest thing to do is to multiply by the base and add the digit repeatedly. So I guess I'll go over a quick example of what that actually would look like. So let's say your digits are 1, 2, 3. So you want your number to be 123. So first you have x equals 0. Then you do 10x plus 1, which gives you 1. Then you do 10x plus 2, which gives you shift the 1 over, and then you add the 2 at the end, so that gives you 12. And then 10x plus 3 gives you 123. So the reason this is nice is you don't have to like find different powers of 10 and multiply by each of those. Can you show how that can be solved for large constraints? C was quite easy, while D was... Yeah, I actually found D pretty difficult because it had a lot of like kind of edge cases in the implementation. So I actually got wrong answer on D like 3 times, which is a little new. I think D actually took me longer than E and F combined, maybe. Let's see. Yeah, so D took me like 13 minutes. Oh, I guess not compared to these combined, but this took 9 minutes, and this took, I guess, another 18 minutes. So D was definitely up there for me. In terms of how to do this for large constraints, I'm actually not sure. I haven't really thought about it. That's definitely an interesting question. One other thing to note is it is really important to read the constraints. Frequently when they give you constraints, realizing that the constraints are small can give you a much simpler solution. And during a contest, you typically don't want to implement a solution that's faster if it's harder to think of or harder to implement. You basically want to implement the easiest solution you can that's fast enough. You don't want to do extra work or have an extra chance of mistake to try to make your solution even faster. Oh, will it be recorded after the stream? Yeah, it should be. I think it should just automatically turn into a YouTube video because I'm streaming on YouTube. And I think you should be able to rewind and fast forward during the stream live. Can someone check if that actually works? Are you able to rewind? This is my first time streaming on YouTube, so definitely let me know if there are any tips or tricks that I should be aware of. Okay, awesome. Thanks for letting me know. Great, so let's solve D. Alright, one person says rewind doesn't work, so that's very unlucky for them. Oh yeah, should I pin a message? I guess I can pin a message saying what we're going over. Oh, I guess it's in the description anyway, so it's not really important, but I'll pin it just in case it helps anyone. I hope I pinned the right message. Okay, cool. So let's do problem D. This is definitely actually a pretty tricky problem, I thought. So let's look at some of the examples. So basically we're given a string, let's say 1, 2, 3, and then we're given an integer m, say x equals 1, 2, 3, and m equals, let's say m equals 40. Yeah, okay. So what we want to do is, hold on, some people are saying that's not working and update. Let me know if there's anything that I should change. Okay, so what we want to do basically is we can consider this as a number in any base we want, as long as that base is 4 or higher. The reason we can't do like base 3 or whatever is because the digit 3 doesn't actually exist in base 3. Yeah, it was kind of funny that they had 12 test cases with length equal 1. Or maybe more, actually. So we basically have here our string. Okay, so let's consider this in different bases. For example, 123 in base 10 is just equal to 123, right? Because we were writing all the numbers in base 10 unless otherwise specified. 123 in base 4 is going to be 16 plus 8 plus 3, which I guess is 27. And then 123 in base 5 is going to be 25 plus 10 plus 3, which is 38. And then 123 base 6 is going to be 36 plus 12 plus 3, which is some number greater than 40. Okay, so the idea here is we want to count how many bases give us a number that is less than or equal to m. So you'll notice here that they form kind of a continuous interval. Every time you increase the base, you increase the value of your number. And you can see that because if you consider the base to be b, this, for example, would be b squared plus 2b plus 3. For whatever you plug in as b. So all of these are non-negative. So this is like an increasing function of b. So this leads us to the idea of binary search. So what we want to do is we want to find the smallest base b so that this number is bigger than m, and that gives us our upper bound. So that would find us like 6. And then the answer here would be like 6 minus 4, because there are two possibilities. So let's look at the code, and then we'll kind of discuss some of the edge cases, since it's definitely important to be aware of those. So first, I just read the input, and to make things easy, instead of using a string, I want x to be an array of the digits values. So first, we actually have an edge case here, right? So if size of x, so this is actually kind of interesting. This is how many different integers can be obtained, not how many different bases can be obtained. And I kind of glossed over that here, because here I counted how many different bases you can use. The reason this is the same is because the value changes whenever you change the base. So every different base gives you a different value of the number. The exception is when you have a one-digit number. When you have a one-digit number, the base doesn't affect the answer. Right, like 3 in any base is just 3. You can see that here, right? The last digit doesn't have any factor of b in it. So this gives us an edge case where we have, if you only have one digit, then the answer is either 0 or 1. If that digit's larger than m, for example, if you have the string 7 and m is 5, the value is 7, which is greater than m, so there's no possibilities. Otherwise, there's exactly one possibility. So we knock that case out early. Then here, we have this function, which given a base, evaluates the polynomial, right, to evaluate the value of the number. And here we're using the same kind of trick that we used in a previous problem to convert a list of digits into an actual value in a given base. And it tells you if this is greater than m, then say that, yes, we've reached something greater than m. And after that, we simply binary search for the first base that gives you something greater than m. And then there are some more edge cases here. First of all, this could actually overflow because m can be very large. So if your base is large, you can jump straight from something less than m to something greater than the largest possible 64-bit int. So in order to avoid this overflow, we use this check. So if you use division here, this is basically a rewriting of res times base plus I greater than m, but this will never overflow. So this is like a safer way to do it. And I actually got wrong answer because of this. Another edge case is if the largest base is actually, sorry, the smallest invalid base is actually more than the lower limit, which is the maximum digit plus 1, then this number we calculated could be negative, so we want to just make sure this number becomes 0 in that case. Yeah, so those are the edge cases. I guess one more thing is make sure you don't plug in 0 here, because then this will blow up. Division by 0. Someone said, when string equals 4 and m equals 9, why is the answer 1? Good question. Yeah, so this is kind of what I was explaining earlier, where if the string is 4, no matter what base you pick, the value of the number will be 4. And as a result, 4 is the only value you can get, and it's valid because m is 9, so 4 is less than or equal to 9. So that's basically that. It's just 1. Cool. Alright, let's go over E. Okay. So E was kind of an interesting problem. So you basically have, right, so this is a graph problem. You can consider each city to be a node, and you want to find the shortest path from city X to city Y. The only kind of tricky part of this is that the time it takes to get from city X to city Y actually depends on how much time you've taken so far. The reason for this is, let's say there's a train that goes from city A to city B every 10 minutes. So that would be k equals 10. And then let's say this train takes 5 minutes. So if you arrive at A at time 0, you'll get to B at time 5, so you effectively took 5 minutes to get from here to here. But if you arrive at A at time, let's say, 5, or actually, let's say you arrive at time 3, then you actually have to wait 7 minutes for the next train, and then it takes 5 minutes. So that would end up giving you 12. By the way, I have kind of a random question for the people in the chat. For those of you who are watching me here, have you already watched my Twitch streams in the past, or are you new because of YouTube? And did anybody find this via like the YouTube feed as opposed to like Code Forces or something like that? Okay, so this is kind of our setup, and it turns out we can actually use Dijkstra for this. This uses kind of a weird form of Dijkstra that I haven't actually used before, so I was excited to be able to use it. But basically, if you want to use Dijkstra, your condition is something like you have your Dijkstra. You can kind of think of a little bit like a DP. So for each node, you have the minimum cost to get there, and then you have a way to extend each node to get the cost to get to the next node. And the cool thing is this extending thing doesn't just have to be addition. Yeah, a lot of people are saying they've watched on Twitch before. And someone said, why aren't you doing it on Twitch? Yeah, I just thought I would try out doing YouTube. It seems like there are probably some pros and cons to both. So far, it seems like a lot fewer people are finding me on YouTube, because I normally have a lot more viewers than this on Twitch for these streams. So I might switch back to Twitch, but we'll see. I feel like the chat is also a little bit more engaged on Twitch, but maybe that's just because there are more viewers. Okay, so it turns out that for Dijkstra, what you want to do is you kind of have a few conditions. You have so if you have 2 paths, let's say path 1 and path 2, and you want to extend both of them by a certain edge, let's call it E, and you know that path 1 is better than path 2, then you also know that path 1 plus E is going to be better or at least as good as path 2 plus E. Which means that once you find the shortest path to a node, you don't need to consider any other paths to that node. Right? So this is kind of how Dijkstra works. And then the other thing you need is adding E never decreases your path length. Yeah, so once you have those two conditions, you can actually use Dijkstra. So this is actually a pretty interesting problem because I believe those conditions are sufficient. So I actually used Socketh's Dijkstra code, which I kind of like laughed about it before because when you use it for just standard Dijkstra, it tells you to pass in like how you define less than, and what the type of a path is, and what the type of an edge is, and what the join path and edge is. And normally these are all just like ints or like plus or like less than. But it turns out in this problem there's actually some value in using something special. So here for the edge weights, we need to know the time, and we also need to know how frequent the train is. And if you have a path that took you time minutes already, then what you do is when you want to add an edge to the end, you don't just add t, you have to round it up to the next multiple of k, and then add t. And this actually satisfies the Dijkstra properties that we laid out on the whiteboard. And this actually reminds me of problem A, right? Rounding up to the next multiple of k, just with the edge case is slightly different. So once we do this, this is actually all we need. We can just do a standard Dijkstra once we kind of frame our stuff in this weird way. And, you know, I'm a big fan of using pre-written code. It definitely saves you like potential mistakes and time. Can you please repeat how we're taking the edge weights here? Yeah, exactly. So that's kind of the trickiest part here. So the edge weight here is actually like two parameters. It's k, which is when the trains depart, and the amount of time that the train takes. So the edge weight isn't actually a single number. It's like this kind of descriptive struct that tells you the two parameters controlling the train. And then when we want to add the edge weight, we don't just do plus, we use this function, which you'll notice doesn't just add a single number. It actually combines time, k, and t in like a more interesting way than that. But it still satisfies the properties that adding an edge will never decrease the length of a path. And if you have two paths, using the shorter one to start with is always okay. Someone said in the chat that it's ceil of current over k times k, which isn't quite right. Or I guess, like, that's part of the logic that goes into this, but yeah, you can't boil the edges down to a single number here. You have to kind of consider them as this, like, struct. Yeah, and then once we have all this pre-written code, we just, you know, use it, and then if it's not reachable, we print -1, otherwise we print the distance. Cool. So that's E. Now let's go over F. By the way, how's the resolution? Is like the text and the whiteboard readable? I assume YouTube has really good quality, but I haven't actually, I guess, used it for streaming before. Oh, and by the way, if you'd like to stay in touch with my future streams or my videos, for example, I also uploaded a screencast so you can see me coding all these solutions live. You should subscribe to my channel or check out my Discord. Yeah, and I guess if you're not following me on Twitch, you may want to follow me on Twitch because I'll probably stream there in the future as well. I normally stream there. This is just a one-time trial of YouTube streaming, and we'll see what I think of it later. Okay, cool. So this was I thought a very tricky problem. It has a bit of a complex statement, but I kind of like the story. So basically what we have here is we have these different ingredients, and if you mix k different ingredients, then let's say their sum is s, then every second you go through s plus k, s plus 2k, etc. And you want to minimize the time until you reach your target value, which I guess is x. So for example, here they have an example. If you mix 3 plus 8, then k equals 2. And then you can do 11, 13, 15, etc. until you get to the target value. If you mix all of them, you would add 3 at a time. And it turns out that then you'll never reach the target value for this example. And then they actually said under the constraints it can be proved that it's always possible to make a potion. And the reason for that is the ingredient values are all lower than the minimum target value x. And you can pick one ingredient, and if you pick one ingredient, you'll increase by 1 every time. And then you'll hit every integer, so you'll definitely end up hitting x. So at first, this seems like a pretty tricky problem, right? So the way that we're going to solve this is for each k, consider all sums of k elements. And at first, it seems like it's going to be way too slow, right? So for k, you have 100 different possibilities. And when you're considering all the sums of them, you know, that's either like, you can bound that with 2 to the 100th, which is, you know, colossal. Or you can bound that with something like the maximum sum of a, which is about 1 billion, which is also too large. So this seems like it's not really going to work. And then I think you would have to do like a DP that also keeps track of how many elements you've used so far. So it would be like 100 times 1 billion. And then you have to do that for each k, so it'd be like 100 times 100 times 1 billion. But the cool trick here is if you have 2 different possible sums that are both the same remainder modulo k, you only care about the larger one. Because what you want to do is, effectively what we're doing here is we want to find for a given k, we want to find the maximum sum that is congruent to x mod k. So we can use this to optimize our DP, right? K is going to be small. So we only have to keep track of the maximum sum for each remainder mod k, which is only 100 different sums. So then we end up getting a DP that is fast enough. So let's check out the code. So here we're going through each value of k, and then we do a 2-dimensional DP for how many elements are used and what the maximum sum is for each remainder. So this is going to be n times n squared. And then we also have to loop through each element to add it in. So we end up doing an n to the 4th DP, and that's fast enough here. So let's go over how this DP works. Let's see. The maximum sum of I elements that is congruent to j modulo k, or -1 if none exists. Cool. So what we're doing here is basically we want to consider adding each element, and you look at some number of previous elements and some remainder, and if that's not reachable, you just skip it, And if that is reachable, you look at what the new value would be, which is this maximum value plus your new element. And then you set, you're using one higher element count, and the new remainder is next mod k. And you're setting that to the max of its current value and next. The one other thing to note here is we actually have to loop through these in reverse. The reason for that is because if you didn't loop through this in reverse, you would say, well, using 0 elements, I can get a sum of 0. And now, using 1 element that's equal to 8, I can get a sum of 8. And then you would say, well, because using 1 element, I can get a sum of 8, that means with 2 elements, I can get a sum of 16. But that's not actually true, right? So if you put this in ascending order, you could basically use the same element multiple times, which for this problem we don't want. There might be another problem where they have an unlimited supply of each material, and in that case we would want that, but here we don't. So we just make this decreasing so that you don't have that kind of like infinite feedback loop. And then we just evaluate the answer, right? So if this is our starting value, if it's unreachable, you skip it. Otherwise, you do here's how much more we need to add, and here's how much we add each minute. So this is the number of minutes. Cool. So that's the solution to K. Definitely a pretty interesting contest. I liked K because it was actually a very good example of it's really important to read the constraints, because this really small constraint of n less than or equal to 100 is kind of what enabled us to have such a simple solution that actually worked. I'm not sure this would be solvable with a higher value of n, but it definitely would be harder to figure out. Yeah, so overall, I think a pretty fun contest. D was a cool problem, very tricky. I'm curious if there are approaches to E other than using Dijkstra. In this case, I was happy to use this new kind of formulation of Dijkstra that I learned about recently, but maybe it's possible to figure out in some other way. And then F was pretty cool. It's kind of a twist on a standard kind of counting or knapsack DP. But yeah, thanks everyone for joining, and you can check out my Discord and my Twitch in the description, so please subscribe and join there if you're interested. And definitely please subscribe to my YouTube or leave a like if you can. You know, well, if you enjoyed the content and want to see more like it, of course. If you didn't enjoy it, I guess leave a dislike, but please don't. Anyway, thanks so much for joining everyone, and I'll catch you in a future stream.